Hello everybody, welcome to another video in which I try to explain physics as simply as possible but not simpler. And today I will discuss the uniformly accelerated motion. And I also talk about this topic in my level 1 videos, which are more basic for primary school. You can check them here and in the description of the video. So I will begin only with briefly summarizing what I discussed there, and we will move to a little bit more advanced things related to the accelerated motion. So speed is not always constant, of course. Usually we accelerate or decelerate, which means we slow down. So in physics we describe this by the quantity called acceleration. To understand it, let's recall the example. So you have a super fast Porsche or Ferrari car and old track. So both of them can accelerate from 0 to 80 kilometers per hour, but the Porsche can do it in a couple of seconds, whereas the track needs much more time. So this brings us to the definition of the acceleration. So acceleration, A as acceleration, is change in speed divided by time. This triangle is delta, Greek letter delta, and it means delta something means change in this something. So delta V is change in speed. So this is new speed minus old speed. Okay. And we focus on uniformly accelerated motion, which means that acceleration is constant, which is not always the case. And often, for example, you can quickly accelerate from 0 to 20 or 40 kilometers per hour if you are driving a car, or maybe little less if you are driving a bicycle or electric scooter. But then it takes you more and more time to increase more, because you are closer to maximum speed of your vehicle, and there is also air resistance. Okay, and we discussed also how to calculate the distance. So first of all, the graph, how the speed changes with respect to time. And uniformly accelerated motion means that your speed increases by the same amount every second. Okay, so graph looks like this, because for example, after 1 second your speed increases from 0 to 2, after another second from 2 to 4, then from 4 to 6, and so on. Okay, so this is how the graph speed versus time looks like. If you start from speed 0, and distance is the area of the figure below the plot. So this is distance, so this is change in speed, because it's the final speed or speed at some time t, minus initial speed, which is 0. This is time, right? So distance can be calculated as the area of this triangle. So this is delta V times t divided by 2 as area of the triangle. And now look, if you rearrange this equation, you get that change in speed, delta v, is acceleration multiplied by time. And let's plug it in here. So instead of delta v, I can write a t, and now times t divided by 2. So distance can be written like this, but it can be also written as 1/2 a t squared, which for some reasons is sometimes more useful. Now let me discuss more general case in which the initial speed is not zero. So for example, you are driving 50 kilometers per hour, but then you are going into a bigger road and you increase your speed from 50 to 80 kilometers per hour. So the graph speed versus time looks like this. Here is your initial speed, okay, v0, let's call it v0, and you increase your speed like this. And I want to know what's the distance covered in this time. So again, the distance covered is the area below the plot. So this the area of this, and you are right, it's a trapezoid, but I prefer to think of it in another way. Think of it as a rectangle plus triangle. It's just more convenient to do it like this. Maybe the formula is a little bit simpler or more convenient. Okay, so now look, this is initial speed, this is time, and this is final speed minus initial speed. So this is change in speed. So area is rectangle v0 times t, this is area of rectangle, plus I add the area of the triangle. So this is so this is change in speed times time divided by 2. This is triangle, or as I showed you before, this can be using this can be written as 1/2 a t squared. So this is how you calculate the distance in uniformly accelerated motion with initial speed. And now look, if the initial speed v0 is 0, then this disappears and you have only 1/2 a t squared, which we had before for the case with no initial speed. So everything is consistent. Okay, very good. Now let's move to decelerated motion. So the case when you slow down, and it's described in a very similar fashion to the accelerated motion. Okay, so still we have a equals delta v over t, and now it can be called deceleration instead of acceleration. And now what? Now you can think of change in speed now as old speed minus new speed, because now if you decelerate, then you change your speed from, for example, from 80 to 50 kilometers per hour. So old is 80, new is 50, 80 times 50 is 30. Well, you can also keep the previous formula, so it was new speed minus old speed. So in this case you will have 50 minus 80, so you will get minus 30, and that's also fine because in this case your acceleration will be negative, which can show you very directly that this means that you not increase your speed, but you just slow down. So that's fine. And let's focus also on the case of the uniformly decelerated motion. So a is constant. So how the graphs look like? So speed versus time. So let's say we have some initial speed, and if you slow down up to 0, it looks like this. For the uniformly decelerated motion, this is again a straight line. You can see it easily that this is the straight line because look, if we use this equation, a equals, and delta v, let's say this is old velocity, initial velocity, minus velocity at some time divided by time. So you can multiply by t, so it's at equals v0 minus v, and I want to calculate v, so it will be v equals v0 minus at, so you move v here and at here, or it's v equals minus at plus v0. So this is like in mathematics you have, so this is v of t, right? V of t, v being a function of time. So this is as y being function of x. So this is ax plus b, which is a linear function. So this has to be the straight line. So now more general case. Let's focus on more general case. So again, speed versus time. You start from some initial speed v0 and you decelerate to some new speed v1, and then maybe you keep going with the constant speed. And the question is, what's the distance covered when decelerating? So in this time interval. So again, the distance is the area below graph, so something like this. And again, you can say that this is a trapezoid. It will be correct, but let's do it another way to show you that the formulas for distance in accelerated and decelerated motion are very similar. And I will surprise you. Let's think of big rectangle like this, and if you subtract the area of this little triangle, then it's equivalent to the area of the trapezoid. Yeah, it's a bit tricky, but let's do it this way. So the distance is the area of this. And look, maybe look. So this is v0. This is delta v, okay? Change from initial speed to final speed is delta v, and this is of course time. So distance, area of the rectangle, so this is v0 times t minus area of little triangle, so delta v times t over 2. So this is big rectangle, this is little triangle, and again this you can convert as previously to be 1/2 at squared. And now you can compare with formula for distance in uniformly accelerated motion and see that they are exactly the same. The only difference is this sign. Okay, that's all for now. In next video I will show you how to apply this uniformly accelerated and decelerated motion in solving some problems in physics.